In this lecture, we're going to talk about binomial probability distribution. First, look at some criteria of binomial probability distribution. It is a probability distribution for a discrete random variable x with the probability p of x such that the following conditions are met. The sum of all probabilities is 1. Any probability has to be between 0 and 1 inclusive. It has a fixed number of independent events. Each event has only two outcomes, one considered success and the other one failure. And the probability of success and the probability of failure remains the same for all events. Now let's look at some binomial probability distribution notations. We should have independent trials, and the number to represent that is n. We're interested for a certain number of successes, and that would be x. The probability of success in any of the trials is p. The probability of failure in any of the trials is q, where p plus q is always equal to 1. Once these notations are identified, the binomial probability distribution formula goes as follows. NCX, p to the x power, and q to the power n minus x, where x, the number of successes, goes from 0 all the way to n, the number of trials. Let's look at some examples. We're given a binomial probability distribution with n equal to 25, p equal to 0.8, and we want to know what is the probability when x is equal to 18. So we have 25 independent trials with the probability of success is 0.8, and we want to know probability of getting exactly 18 successes, where x is 18. We first find q. Then we're going to use the binomial probability distribution formula. So that would be 25C18, which calculates the number of different combinations that this can occur. P to the x power times q to the n minus x power. We do the calculations, and that probability is 0.1108. For most part, you can round all the probabilities to 3 decimal places. From time to time, I keep it here at 4 decimal places, or I round it to 3 decimal places. In this example, we're given a binomial probability distribution with n equal to 100, p equal to 0.5, and we want to know probability that x is equal to 45 or x is equal to 46. We should first realize that probability that x is equal to 45 or x is equal to 46 are two mutually exclusive events, which means we find probability that x is equal to 45 plus probability that x is equal to 46. Now we use the binomial probability distribution to find each one, with q equal to 1 minus p, which becomes 0.5. So probability that we get exactly 45 successes using the formula will give us 0.0485. And we do the same thing for probability of exactly 46 successes using the binomial probability distribution formula, and we get 0.0580. Now to proceed, we add these two probabilities together, and the final answer is 0.1065. If I was going to round these to 3 decimal places, the answer would have been 0.107. Now in this example, we're looking at a binomial probability distribution with n equal to 20, p equal to 0.2, and we want to find probability of at least one success. The keyword here is at least one. So probability of at least one, as we know from before, is 1 minus probability of none. So if we let x to be the number of successes, then at least 1 will be probability that x is greater than equal to 1, which is equal to 1 minus probability of none, so that means x has to be equal to 0. With n equal to 20 and p equal to 0.2, we use the binomial probability distribution. We do the calculation, and the final answer is 0.9885. Now here are some binomial probability distribution keywords. Exactly, at most, at least, fewer than or below, more than or exceed, between A and B inclusive, from A to B. So when we're doing this kind of problems, we need to keep track of the keywords and how to translate those into mathematical notation. Now, when working with probability that x is less than a or x is greater than a, it's strongly recommended we do the following. For probability that x is less than a, we do probability that x is less than or equal to a minus 1. And for probability that x is more than a, we use probability that x is greater than or equal to a plus 1. We will visit this in some examples and explain that again. So let's say you're about to take a multiple choice test with 20 questions. Each question has 5 possible choices, but only one choice is correct. If you were to guess randomly on all questions, what's the probability of guessing exactly 3 correct answers? What is the probability of guessing fewer than 4 correct answers? And what's the probability of guessing at least 3 correct answers? So we realize that n is equal to 20 because there are 20 questions. P is equal to 1 over 5 because there were 5 choices with one correct choice. And Q will be 4 over 5, which is 4 wrong choices out of 5 all possible choices. So now what's the probability of guessing exactly 3 correct answers? So the keyword exactly tells us we want probability that x is equal to 3. Using the binomial probability distribution formula, we get 0.205. Now, probability of guessing fewer than 4 correct answers. So fewer than 4 correct means probability that x is less than 4. So if it's less than 4, so it has to be less than or equal to 3. And less than or equal to 3, we need to find probability that x is equal to 0, probability that x is equal to 1, probability that x is equal to 2, plus probability that x is equal to 3, and we add them all together. So if we do those calculations and add them together, that probability is 0.411. Now, what's the probability of guessing at least 3 correct answers? So at least means greater than or equal to. We use the complement rule, and probability that x is greater than or equal to 3 is 1 minus probability that x is at most 2. So at most 2 will be less than or equal to 2. And less than or equal to 2 will be probability that x is 0 plus probability that x is 1 plus probability that x is 2. And we find this total and subtract that from total probability 1. So we do the calculations and the final answer is 0.794. Now, an airline claims that 96% of passengers with tickets actually show up for their flights. So they're going to overbook a flight by selling 145 tickets for an aircraft that has 140 seats. What's the probability that the number of passengers with ticket who show up is between 135 and 140 inclusive? So we know that n is equal to 145, p is equal to 0.96, q will be equal to 0.04, and we want the number of tickets that show up to be between 135 and 140 inclusive. So we add all the probabilities starting with 135 successes to 140 successes, and the final answer for that is 0.661. So we have to use binomial probability distribution for each number of successes and add them all together. Now we want to know how to find binomial probability using TI. First, we're going to make a table. We take the given information and we find out what n is, what p is, and what x is. Then we press second, followed by vars. We arrow down several times to find binomial PDF or binomial CDF. I will show you how to use those in a few moments. We enter the values for n, probability p, and the number of successes x to complete the following commands. binomial PDF, NPX. Those numbers are separated by comma. Again, I will show you how to do that on a TI calculator. Or similarly for binomial CDF. And then we press enter. Now, how and when do we use binomial probability distribution when using TI? If we have exactly, we use binomial PDF, and any other situations we use binomial CDF. And once again, when working with probability that x is less than a or x is greater than a, we do the following. When x is less than a, that's equivalent to x is less than or equal to a minus 1. And when x is greater than a, that's equivalent to x is greater than or equal to a plus 1. So let's look at some examples now. We have a binomial probability distribution with n equal to 25, p equal to 0.8, and we want to know probability of x equal to 18. Using TI, the command will be binomial PDF because this is x equal to 18 with those numbers for n, p, and x. And the answer is 0.1108. Now, probability of getting tails when a loaded coin is tossed is 0.6. Suppose you toss this coin 100 times. We want to know, find the probability of getting at most 65 tails. So the keyword at most means less than or equal to. So if x is the number of tails, then probability of getting at most 65 tails is probability that x is less than or equal to 65. Using TI for less than or equal to is binomial CDF with n, p, and x entered. And the answer is 0.8697. You're about to take a multiple choice test with 40 questions. Each question has 4 possible choices but only one correct choice. If you were to guess randomly on all questions, what's the probability of guessing fewer than 15 correct answers? What's the probability of guessing more than 10 correct answers? And what's the probability of guessing between 8 to 12 inclusive correct answers? And what's the probability of guessing fewer than 8 or more than 12 correct answers? So we obtained that n is equal to 40 and p is equal to 0.25. So getting probability of guessing fewer than 15 correct answers means x is less than 15. But x less than 15 is the same as x is less than or equal to 14. So we use binomial CDF. We entered n, p, and x. The answer is 0.9456. Now, the probability of guessing more than 10 correct answers, that means x, the number of correct answers, would be greater than 10. Greater than 10 means 11 or more, so x has to be greater than or equal to 11. Here we have to use the complement rule, so that is equal to 1 minus probability that x is at most 10. Using the TI, we get 1 minus binomial CDF with n, p, and x. And the final answer here is 0.4161. Now, what's the probability of guessing between 8 to 12 inclusive correct answers? So in this one, we have to use the binomial CDF twice. First, we use for the right-hand side number, the 12, the larger one, minus another binomial CDF with the smaller number, minus 1. So the smaller number here is 8. 8 minus 1 will give us 7. We use the TI calculator to complete this task, and the answer is 0.6389. And finally, what's the probability of guessing fewer than 8 or more than 12 correct answers? Fewer than 8 will be x is less than 8, or more than 12 correct answers, so that would be x is greater than 12. So I'm going to subtract what is in between from total probability 1, and that will do the trick for us, which is 1 minus probability that x falls between 8 and 12 inclusive. Using the previous answer, the final answer is 0.3611. Now, I hope this presentation helped you understand binomial probability distribution. I'm going to continue this with using TI to verify some of these answers. Okay, let's use our TI calculator to do some of these binomial probability distribution problems. The first one, I want to find binomial PDF with n equal to 25, p equal to 0.8, and x equal to 18. So I'm going to press second followed by vars. I'm going to arrow down until I find binomial PDF. My x is equal to 25. My p is equal to 0.8. And my x is equal to 18. I paste that and I hit enter. Now, if you do not have a menu, you basically enter the numbers after the command appears, separated by comma, which is directly above 7. Now let's find binomial CDF with n equal to 100, p equal to 0.6, and x equal to 65. So I'm going to go second vars, arrow down to binomial CDF, press enter. My n, the number of trials, is 100. P is equal to 0.6, and X is equal to 65. And hit enter. So the answer here is 0.8697. Let's continue by doing a couple of more examples, but this time I'm going to do it without having a menu when I use binomial CDF. So I want to compute 1 minus binomial CDF with n equal to 40, p equal to 0.25, and x equal to 10. So I go 1 minus second vars. I'm going to arrow down several times until I find binomial CDF. As you see, there is no menu here, so my n is equal to 40, comma. My p is equal to 0.25, comma, and comma is directly above 7, and my n is equal to 10. I'm going to close these parentheses, and I'm going to execute this by pressing enter. So the answer for that is 0.4161. Now I want to do binomial CDF minus another binomial CDF. So let's go ahead and clear the screen first. So for the first binomial CDF with n equal to 40, p equal to 0.25, and x equal to 12, I go second vars. I arrow down until I get to binomial CDF. Select that. My n is equal to 40, comma. My p is 0.25, comma, and my x is equal to 12. I close this parentheses. Now I want to do minus, so I press the minus sign, which is directly above 7. Now I want to do a second binomial CDF, so I go second vars. I go down until I find binomial CDF, so arrow down several times. I select the binomial CDF by pressing enter. So my n was equal to 40, comma. My p was 0.25, comma, and my x now is 7. I close this parentheses and I hit enter to execute this. So the answer to this one is 0.6389. I hope this presentation helped you understand about binomial probability distribution, how to use your TI calculator to do binomial probability distribution, and also when to use binomial PDF or binomial CDF.